Hello, everyone. Thank you so much for attending this talk. I know it's a really jam-packed slot, and there were lots of good options, so I'm really honored to have anybody at all come to learn about memory management in Python. My name is Eli. I've been writing Python for about 7 years now, I think, and I love it endlessly, love the community, really honored to be here. So this talk is about what pointers are. I'm going to use a definition that's perhaps slightly different than what you see in C and C++, as sort of an abstraction for this talk. I'm going to talk about what Python objects IDs are, why they're useful, where you'll see them come up. And we're also going to cover how CPython can tell when you're done using an object in memory and what happens next. I'll try and keep it tight because we don't have that much time, and hopefully there'll be some time left for questions at the end if there are any questions. Wonderful. So, what is a pointer? Has anyone written C? Is anyone sort of familiar with C pointers? That will help you understand this talk, but I'm going to use a very slightly, you might take issue with my definition of pointer, but I hope you'll forgive me for the sake of the talk. Let's use an example. Here's me, and there are various ways that you can refer to me. I have a name, my name is Eli, but that's not the only way that you can refer to me. I'm also on Twitter, unfortunately. I'm also on Reddit and on Discord under that name. And there are lots of other ways that you might use words to refer to me. All of these things are pointers to me. When it comes to Python, here's what I mean. In Python, we have variable names. We sort of say, my object equals this. And those are entries in Python's namespace. And there are differently scoped namespaces when you're working in Python. Today, we will just be considering the global namespace to keep things simple. And those entries in the namespace correspond to objects in memory, like this. You'd have a variable name, and then you'd have the object in memory that's actually pointed at by that variable name. And what I mean by a pointer is this connection, right? The thing that makes this refer to this. That's what I mean by a pointer, that connection there. And where we see them in code, we have things like, we have variables, and we can see what's in our namespace by calling this globals function, specifically the global namespace. So when we call this globals built-in function, we get a dictionary of all the things we can type into our interpreter that the interpreter understands. And you can see that having defined these two variables, those names are in the global namespace. And we'll use this built-in to inspect the namespace at various points through examples throughout this talk. Another example that we're going to be using a lot in this talk is that of a list. And this is a list in Python. It's a visual representation. And what we have is we have our variable name here, and that points to a list object in memory. And within that list object, there are more pointers. And this makes lists very useful for examining the behavior of memory in Python and showcasing various ways that it behaves. Right. First thing I'd like to talk about is pointer aliasing. And this is a behavior that you see in Python where the value of an object changes even though you didn't actually change it yourself directly. So we'll look at some examples. Here we have a list that I'm defining. My cool list, just a list of 3 strings. Printed it back out there and said, okay, we have a list. This is now an object in memory. But I'd like to make a copy of this list and change it from my cool list to my amazing list, right? Or my awesome list, sorry. So I say, okay, well, let's have B. And B is the same as A, but I want to change B. And now I've replaced cool with awesome. And this is great, and this is wonderful, but what we'll find, and what often confuses people who are new to Python, is that A has changed as well. Has anyone else ever seen this behavior and been confused by it? Yeah, a handful, right? And this is called pointer aliasing. Now, we can get around this in lists because lists have a copy method on them. And we can say, okay, actually what I want to do is I want to make a whole new copy of my list. So I can do that. I can call this copy method. And I can say, okay, let me make C, which is a new copy. And then when I do the same thing again and I change from awesome to amazing, we see that our original list was left unchanged by that operation. And the reason for this is that when we set B equal to A, all we're doing is making a new pointer to the same object in memory. And when that object in memory is changed, whether or not you do that by calling it B or A, the same change happens. if Eli dyes their hair purple, then that knitter who sits in the front row of the conference also has their hair dyed purple, right? But when we do a copy, what we do is we make a new list object in memory, and we can change that without affecting the original. But what if we put pointers inside our pointers? Here's another example. We have a new list, and this is a list inside a list. So we've got the outer list, which is this one that includes the 42 at the end. I just put an integer in there to make it clear that there's two levels. And then the inner list is this list of names. And so we can do the same thing again. We can say, okay, I'd like to make a copy of that list so that I can change things without changing my original list. And so I do that, and I'd like to add Charlie to my list of names. And when we do that, we can say, okay, I want to access that first element of my new copy of the list, and I'd like to add a new name to it. That's what we're doing when we do append to B0. So I do that, and I print it out. But then I look at the original list, and the insides of that original list have changed as well. Has anyone seen this before? Yeah. And the way you get around this is with, what happens if it's pointers all the way down? How can I make an entirely new copy without changing the original if I've got a list inside a list? And the way around this is a method called deep copy from the copy built-in part of the Python standard library. And what you do is you make a deep copy of your original thing. And what this does is it makes a new copy of that outer list structure, which is what the regular copy was doing, but it also makes new, fresh copies of everything inside it. What was happening with the regular copy is it made a new outside, but it still pointed to the same inside. So what we can do is we can do a deep copy, and then in our new deep copy, we can append another name, and we can see that that hasn't changed the original. I've got some visuals coming up to help explain this because it's pretty abstract. What happens when we set B is equal to A? You've got this list object in memory, and there's A, and that's what happens when you first define it. Then, when we do B equals A, we add a new pointer here, right? When you use the copy method, a shallow copy, not a deep copy, this was our outer list, and this was our inner list of names. We had the original object, and we did a copy, and it made this new object, but deep down underneath, it was pointing at the same list on the inside. It made a new, 42, that number that I put in there just to show that there was a list inside a list. But the list that was inside the list is the same one. So when we appended Charlie to it, it was reflected when we looked at A. Deep copy makes a new object entirely, and you can see that there is no connection between the new one and the original one. And it will do this no matter how many layers of objects within objects you have. And sometimes you want this, sometimes you want to use this, because you won't have any pointer aliasing when things change without you expecting. But also, this is not very memory efficient, right? If you're working in a memory-constrained environment, you might not want two whole copies of the same thing floating around. So, knowing how and when to use this will be dependent on your context, but it's good to know how it works. Now, in the abstract, I promised you some tuples behaving badly, and this is a really funny example of a weird behavior that Python has that I'd like to show you. So what we have is a tuple is an immutable object. And this means that once you've defined it, it cannot be changed. So once you say, okay, I have a tuple, and these are the elements of my tuple, those elements can't be swapped out after the fact. But you can have those elements be pointers. They point at objects. And what that means is, so if you have a pointer as one of the elements of your tuple, you might not be able to change where that pointer points, but you might be able to change the object that it's pointing at. If it's pointing at something mutable, then we can get some really funny behavior. So the example I'm going to show you is this. We have a tuple, and inside our tuple we have a list, and lists are mutable. You can mutate them in place. So here we have a tuple A. You can see the pink rounded brackets to show that it's a tuple and not a list. And the first element is a list. We've just printed it out there. And I can do things to this list. I can append numbers to it, right? And this is fine. This is good. We can do this. And once I do this, you can see that it's happened. Nothing unsurprising here. But with lists, there's multiple syntax options that we have for appending to the end of them. We could also do this, right? That's basically the exact same, except we're adding 4 instead of 5 instead of 4 at this point. But if you try and do this when the list that you're trying to append to is an element of a tuple, you get this. And this isn't that surprising because, you're doing a sort of plus equals here. You're trying to assign to A0, and tuples you can't assign to their elements. So it's normal and expected that we would get this error, right? Error tuple object does not support item assignment. We're trying to do an equals here to that A0, and you can't do that with tuples. They're immutable. Still, no surprises, kind of annoying. You have to use a particular syntax. But if we now look at our list that was inside the tuple, it does have that 5. That 5 is there. Python was like, no, you can't do that, but I did it. But you can't do that, but I did it. Why does this happen? Well, it's to do with the plus equals operator. What this is doing is it's doing kind of 2 jobs in one. First, it's adding the number 5 to the end of our list, and that happens, no problem, because we can append to lists. But then what it also does is it tries to assign that list back to itself. And that's where we have a problem because we're using a tuple. The reason that the plus equals operator has this behavior is because it doesn't only operate on mutable objects. When you're working with mutable objects, that assignment at the end is a non-op. It doesn't do anything because you've already mutated the object in place. But if you're using this with strings, which are immutable, what it actually does is it adds those 2 strings together, which creates a new object in memory, which it then has to reassign the previous variable name to that new object. So the equals is doing something. But the reason that we see this strange behavior is that when you do plus equals, it fails halfway through that operation. It can do the plus but not the equals because our list lives inside a tuple. And that's why we get this weird behavior. But this is sort of if you look at sort of strange Python gotchas, this is one of them, and that's why it happens. So back to pointer aliasing. We've got this situation, right, that comes up fairly often where you have one object in memory and it's got a name, and maybe it's got another name, but you don't know, just by looking at what's available to you in your interpreter, whether or not these 2 things really refer to the same thing under the cover. How can we find out? Well, this is where object IDs come in. And an object's ID in Python, you can find it by calling another built-in. You can just call this in, this is part of the Python specification. Every implementation of Python should have this function available to you. And what this does, when you call it on any object, it'll return you a number that is unique to that object. It is constant for as long as that object exists in memory, for across the entire lifetime of that object in memory. So many Python implementations do this by using the object's address in memory as its ID, because that's something which has to stay constant while the object is alive, while it's available in memory. It's something which is unique to the object. 2 things can't live in the same place in memory. But not all Python implementations can do this. CPython does this, and that's what I'll be using examples from for the rest of this talk. But not all Python implementations have access to that. Sculpt is one. It's a Python to JavaScript transpiler. And because it runs on the JVM, it doesn't have access to stable memory addresses. So what Sculpt does when you call IDX on an object is it just generates a number, one more than the last time when you called IDX on a different object, stores it in memory, attaches it to that object, just generates and caches a new number to be the ID. It's got absolutely no relationship to the memory functions, memory properties of this object, but it must satisfy the conditions of being unique and constant for the lifetime of X. So let's have a look at some IDs. Got a list. We like lists. It has an ID. This example is from CPython, and IDs tend to look like this. If you come from the C world, you'd probably be more familiar with this as a pointer if you saw it written in hexadecimal, but Python interpreters by default put them out in binary, in decimal, not in binary. And if we set b is equal to a, as we have done in previous examples, you can see that when we look at their IDs, they're the same number. These refer to the same object in memory, right? And we know this because when we set b equal to a, these are just pointers to the same object. If we do what we've done before, make a copy of that list, they have different IDs. They're different objects in memory. Now, when we want to look at whether or not 2 objects are the same, we've got a couple of ways we can do this. One of them is saying A is B, and that'll return you true or false. And what that's doing, that is comparator, is it's just using the IDs. This is equivalent. These two statements are exactly the same. It's just a bit of syntactic sugar. All it does is it wraps the ID calls. And what we can do is we can inspect our little example here using this setup where we've got A, B is equal to A, and then C is a copy of A. And we can look at what happens when we compare these things. A is B, that's true. They're the same object in memory, they have the same ID, we just saw that. And A is not C, A is C is false. Because it's a copy, different ID, no surprises. This isn't the only way, though, that we can compare two objects for equality in Python. We also have the double equals comparator, and this is often more commonly used. And under this comparator, we do have A is equal to C. So these two things do different things. So how can we understand the behavior of the double equals operator? Clearly, it's not just doing the same thing as this. Well, it uses a magic method. Now, we need to understand what's happening there. I'm assuming that most people are familiar with at least some magic methods of objects, things like str, which defines how an object will behave when you call the str built in on it. We've got a deletion magic method, which we'll see a little bit later when we start talking about object lifetimes. And, of course, init. And these are all methods that define how Python objects interact with sort of certain features of the Python language, like having a string representation or being deleted from memory, or being created, like with init. And what the equals magic method is it defines how objects interact with that double equals comparator. So what the equals magic method does, and it's just a method, you can just write to it like you can with any other Python method. It allows you to alter what happens when you do when you use that double equals comparator. So you can do some really fun, weird stuff with this. So this is an example. We've got a user-defined class here, and all I've done is I've defined that magic method, and I've said, okay, we're going to be comparing this with some other object. And all I'm going to do is I'm going to fall back to that ID comparison. I'm going to say, okay, we're going to use that is operator. These things are only the same if they have the same ID. This is actually the default behavior for any user-defined Python class. Me writing this method, I might as well have not have done it because that's what's going to happen anyway. But we can also do other fun things. Here, I've got a class where I've given it a name attribute just so we can tell separate instances apart. And I've said with that equals comparator, that equals method, always return true. No matter what comparison we make, let's say it's always the same thing. And what this leads to is behavior like this. I've got A and B, and I've given them names so that we know that they are different objects. They've got, A name is not the same as B name, but when we use that double equals comparator, they're apparently the same thing, and that's because it's using that behavior. No way, am I in 2 minutes? What? Oh, okay, because it's 25 minutes. Okay, fine. Cool. Yeah, everything will always compare true. You can do the opposite. You can say, let's always return false. And you end up with a class that's not equal to itself because the equals comparator has said, let's always return false. Right, object lifetimes. Python frees memories in two ways. We've got reference counting and we have the garbage collector. Reference counting basically keeps track of how many pointers each object has to it. If there are no pointers to an object, we can't get it anymore. It's useless, it's removed from memory. We can see examples of this by inspecting what happens when an object is freed from memory, and this is where that magic method comes in. This is a magic method is called when an object is about to be removed from memory. It doesn't do that job itself, but we can use this to inspect the behavior. So I've got a named class again, and all I've done is I've hooked into that magic method and said, I'd like to know when this object is about to be deleted. Let's make a Dave, and let's delete him. We make an object, we give it a pointer, we remove that pointer, that reference count falls to 0, and Dave is deleted. If we do a different class, we can say Alice, we give her another pointer. When we delete the first one, her reference count, it was 2, now it's 1. If we want to get rid of her, we have to delete the second pointer, and now Alice is removed. But if you make objects point to each other, there's a way that you can stop their reference count from ever falling to 0, and this is a problem. looking at things, whether or not things are in the namespace again, we'll do that. And you can see that that class we've defined is in the namespace. Now, let's make 2 instances of that class, and we'll make them point at each other, because we can do that in Python objects. We can just add arbitrary pointers to them. And now we've got Jane and Bob both accessible from the namespace. But we can delete those pointers. But their reference counts don't fall to 0 because they're pointing at each other, even though we can't access them from the namespace. What's happened here is we've done this. We've got 2 objects, each with their own name, made them point at each other, so now they each have 2 arrows pointing to each other, 2 references. We get rid of the original ones. These are now inaccessible from the namespace. We can't use them. They should be removed. But the reference count is not 0, so they're not removed. Reference counting isn't sufficient. This is where the garbage collector comes in. And what that does is it detects this scenario and fixes it. And I'm gonna skip through how it does this. It's really interesting. The garbage collector tracks objects, and it knows which objects point at which other ones using this traversal method. The slides will be available, so don't worry that I'm skipping through things. What it does is it's able to detect this scenario where we have cyclic isolates, cycles that are isolated. And we're doing that here, we're setting it up. And what we can do is we can run the garbage collector intentionally. What it does is it finds those scenarios. It calls all of those finalizers, that del magic method, so we get these printouts here, and then it prints out how many objects it was able to remove from memory by removing that cyclic isolate. And in this case, it's 4, because each of our named classes was an object, but they also had a string attached to them, their name. So that's 2 objects per named class, so 4 objects in total. And what you can do as well, and this is, I know I'm almost out of time, so I promise I won't overrun too far. You can actually use those finalizers to do some really broken behavior, because when the garbage collector finds a cyclic isolate, it calls all those finalizers just to make sure that, because sometimes you use them for things like closing a file that you might have opened during the creation of the object or something like that. So Python will call, CPython in particular, this is CPython's garbage collector, will call those finalizers just to make sure that everything's tidied up. But you can, hello? Oh, okay, sorry, my slides. But what it does, yeah, when it calls these, you can hook into this step and do some really, really weird stuff. There's this keyword called global in Python, and you have to be really careful with it, because what it does is it creates a new entry in that global namespace from within, from a lower scope, from a smaller scope, and scopes themselves are an entire talk on their own. What this class does is, while the object is being deleted, let's say it's part of a cyclic isolate and it's having this, it's being deleted, it reaches out into the global namespace and creates a new pointer to itself. Now it's no longer isolated and it shouldn't be removed from memory. If we do that, we set up a cyclic isolate with this class and we try and collect the garbage using the garbage collector, it will call their finalizers and we'll get those print statements, but it won't remove anything from memory because during the course of that deletion process, new pointers were created. And now those objects are no longer isolated. And we can see this because in our global namespace, we have a new entry, person. If I go back, that was the name of the new pointer that we made. So now we've broken garbage collection, right? And we can look at that person. Person has a name. It turns out to be Bob because that was the one whose finalizer was called second. And we can see that the Jane object still exists as well because she was Bob's friend. Yeah, it creates a new pointer person in the global namespace and it breaks that garbage collection process. This isn't fatal though, because Python can only call finalizers once. Finalizers for a given object can only be called once, and you can look at the garbage collector and check if an object has had its finalizer called on it. And so if we do collect the garbage again, we won't get those finalizers run because they've already been called, so we don't get those print statements, but the objects are removed from memory. You can do something even worse though. You can make a new object in memory that hasn't had its finalizer called, and this does break garbage collection. But come and talk to me after if you want to know more about this, because I don't want to overrun too badly. Yeah, that's more looking at that scenario. So yeah, apologies for the slightly rushed second half. We've covered where you'll find pointers in Python, some behavior that will arise because of the way that Python handles objects in memory, why it's different to use the is comparator and the double equals comparator. You can mess around with the double equals comparator and it's really fun. Don't do it in production. And we've talked about how objects are removed from memory and fun ways to break that as well. Yep, that's been me. That QR code takes you to a little form where you can leave me feedback if you're so inclined, but please don't feel pressured to. Please go and enjoy coffee or stay for questions. Thank you so much.